small vector in Rm. So I will simply take norms in both places, and this limit should be 0. Okay, so what are the facts about this derivative? One, if it exists, it is unique. Second, if f is differentiable at a, which means the derivative exists, then it is automatically continuous. That is, the function is continuous at a. We also saw the matrix of, okay, so let's write this down. So what is the matrix of, sorry, not T at A. So matrix of f prime of A. So what is this matrix? I simply take the partial derivatives of f. So this is going to be d1 of f of A, d1 of f of A, all the way up to d. There are m directions, remember that is m variable. So dm of f of A. So this is what the matrix is. And this may seem funny, but we can just say that if f is really, remember the target is a vector in Rn, so there are going to be n components. So this is f1 of A, f2 of A, all the way up to fn of A. So f is a column of functions. Now each one of the fi's is just a real valued function. Then the total derivative, we saw exactly what this is. This is the matrix of partial derivatives. So in the first column, I take all derivatives with respect to x1. So they're all going to be del by del x1, all of it evaluated at A, but let me not write that, all the way up to. But what am I going to do? I'm going to calculate these derivatives for f1 up to fn. And likewise, in the last column, they're all going to be with respect to xm, partial derivatives. And again, for the functions f1 up to fn. So, okay, so this is at A, all of those at A. Okay, excellent. And what was the chain rule? The chain rule was, here is an open set U in so if I have an open set U in Rm, and there is a map from this to Rn, such that the image lies in an open set V in Rn, and the dotted point goes to the dotted point here. So let's say A goes to B, and I call this map F. And then there is another map which takes you to Rk. Then we have G composed with F. I can wonder about its derivative. Sorry, this map is G. What is the derivative of this? Come on. So this is the last piece in our review before we will start with new stuff. So what is the derivative?
G dash of f of A composed with f dash of A.
Exactly. So this is going to be composition of linear maps, which is the same thing as multiplication of associated matrices. Very well, excellent. So what I want to say is the following. So okay, so here let me just write this down. So in another color here, let's say it is quite instructive to read the corresponding material from Rudin. As I said, for the derivatives part, I'm going to be following Pramat's notes generally, but also Rudin. It's about the same. And it's quite instructive to compare the treatment of differentiation for the one variable situation and for the multivariable situation. So I'm going to say this, read Rudin chapter 5, which is the ordinary differentiation, and chapter 9, which is multivariable case, multivariable differentiation. And the questions to ask yourself are what results stay the same? If the results stay the same, do the proofs stay the same, like essentially the same, or do the proofs need to be modified? Okay, so what stays same? How do proofs change? For example, chain rule is an example of this. The result stays essentially the same when you understand it properly. And the proofs also stays almost the same in outline at least, but you do have some new ideas that you have to introduce, like the operator norm, for example. Okay, so this is one question. What needs to be modified? For example, today we are going to do mean value theorem, and we will see that it does need to be modified. And then finally, what are the new phenomena? So if you just look at the lengths of the chapters, so compare, it's considerably longer. So there are lots of new phenomena, and so far we've just sort of wet our tools, so to speak. We will see more and more examples to see that the situation is vastly richer than in the one variable situation. Okay, so with this in mind, now let's start doing some new stuff. So today our brief is MVT. So let me write this down. Okay, so but before I do that, there is one special case of the chain rule that is worth mentioning because it does get used a fair bit. So, okay, I should restart recording.
Recording in progress.
All right, so we've basically just seen the definition of the derivative and revised a few things that we did, including in particular the chain rule. So I want to see a special case of the chain rule. So in this case, notice I'm going from m dimensions to n dimensions to k. I want to take a simple case where both the extreme quantities are one dimensional. So I'm going from R1 to Rn and then back to R1. So special case of chain rule. So which is m equals k equals 1. So I have the following situation. So I have the following situation that I have some open set in R, just R1. So let me just take an open interval in R and go from that. I have this function to Rn, and then I go back down to R. Okay. All right. So I have this function G, and the initial function I'm not going to call F. I'm going to call it gamma. This is because it's a somewhat standard terminology. So gamma is a function that takes, so imagine that I have a time interval. The open interval in R is a time interval. So what is happening? For each time I have a position in Rn. So I have a vector which is moving along with time. So I have a parameterized curve in R. So gamma, a parameterized curve in Rn. And again, G is a function that is from an open set in Rn, etc. So what do I have? And let's write this down. So G composed with gamma prime at T. I know exactly what it is. It is G prime of gamma of T composed with gamma prime of T. Okay, but now let's see what this is. All right. So what is gamma prime of T? So notice gamma is just, so let me write down gamma here, R to Rn gamma. So where is T going to? It's going to a vector that depends on time, right? That means each coordinate is just a real valued function of time. So I'm going to call those the components of gamma. So this is gamma 1 of T up to gamma n of T. Okay, so I have written R, but really, I mean, it doesn't have to be all of R. It's just some open intervals. Okay, so let's look at, so the chain rule is giving me those two things, and it's a composition of functions. But when I think of those as matrices, it's just matrix multiplication, right? What is the matrix of gamma prime?
It's a column vector.
It's a column vector. So remember, this is a function from R1 to Rn. So the matrix, the derivative, and so its matrix is going to be an n by 1 matrix. And which n by 1 matrix is it going to be?
The partials of gamma with respect to each of the x's in Rn.
Right, but just pause to consider each gamma 1, gamma 2, gamma 3, etc. I mean, they're all functions of a single real variable, right? So what does it mean to take the derivative of this vector valued function?
Sir, it will just be gamma 1 dash T, gamma 2 dash.
So it is just going to be ordinary derivatives of the ordinary real valued functions gamma i's. That's all that the matrix is going to be. Okay. And if this is not obvious, then you should actually write down the definition and see that this is what it is doing. There is nothing going on over here. So let's write that down. So what this means is that, okay. So this means I'm going to get the corresponding gamma 1 prime of T up to gamma n prime of T. That's what that function is. So now the question is, what is G prime? Remember, G is a function from Rn to R. So its derivative is going to be a matrix corresponding to a linear transformation also from Rn to R. That means that columns of this matrix are just going to be single real numbers. In other words, the matrix of G prime is going to be just a row matrix. What is this matrix going to be? So let's write this down here. G prime of anything. So let's make a letter over here. So G prime of Y. What is the matrix of that? Remember what G is doing? It is taking n different variables and doing some magic with them to produce a single real number. So what is the matrix of this? This is just a special case of the Jacobian matrix that we constructed for the general Mn situation.
These are just different partials with respect
Right.
to different variables.
Correct. The function is only one. There is only one real valued function, namely G. There are no Gi's, right? So this is just going to be partial derivatives of G with respect to x1 evaluated at Y all the way up to xn evaluated at Y. This is what's going to happen at, right? And so, okay, so let me put this on the side here. So I have a little, so, okay, so when I write down this matrix, it's just del G by del x1 up to del G by del xn. And since I do not have space, let me write all of this at where? All of these partials are at what value?
Gamma of T.
At gamma of T. Okay, very good. So nothing much is going on. But now what does it actually mean? You see, I'm multiplying a row vector with a column vector. What is the result? Yeah, multiplying. Yeah, sorry, come again, please.
The number.
It's just a real number. And in fact, we can write down what that real number is. Okay. So you can write down this real number, but I want to now do this a bit differently. Okay. I want to write this as, I want to write, instead of this row vector, I want to think of this also as a vector in Rn. Okay. Now this row vector, the way we write vectors in Rn, it's not a vector in Rn, because vectors in Rn in our sort of nomenclature, they're all column vectors. So let me write this down as del G by del X1 at gamma of t all the way up to del G by del Xn at gamma of t. So I want to do that. And I want to write the other one here, which is gamma 1 prime of t up to gamma n prime of t. And you see what I've written here is nonsense. I cannot do this matrix product. However, there is an operation that does make sense when I write those two column vectors next to each other to get a number. What is that operation?
Dot transpose.
Exactly. So I do the dot product here, right? So this is the usual. So I'm going to write this here. Let's do red. Usual dot product of vectors in Rn. Okay, so what I want to do is I will give this a name. So call this delta G of gamma t. And the name for this is the gradient of the function G at the point gamma of t. So you see gamma of t is, I mean, it's just some point. So gradient of G at the point gamma t. So this is a useful result. And so what did we see? The upshot is the following. The upshot is G composed with gamma, its derivative at t turned out to be the dot product of two vectors. What is the first vector? It is the gradient of G at gamma of t. That's a vector. And what is the second vector? I don't have to write it as a column vector. What is that vector after all?
Gamma prime
Gamma
t.
t.
It's just gamma prime of t. That's all. Dot product with gamma prime of t. Okay. So this is a useful thing to keep in mind. This situation comes up again and again. We are going to see it later today also. Okay, so very good. So I'm going to just assign as an something as an exercise here. So fix X and V in Rn and take the parameterized curve gamma of t is equal to X plus t times V. And take some function, right? So what does equation give at t equal to 0? This is a very simple exercise, but I do want you to calculate this. Okay. And you see, let me just sort of get started. So, okay, so that is for some function G, right? So G is given for a given function G. And so just to get you started, what I want you to do is evaluate both sides independently. You see, G composed with gamma is going to be an explicit quantity, right? Because I have given you the curve gamma explicitly. So just plug in what it is. And G composed with gamma is a function from where to where? Hello.
R to R.
R to R.
R2, remember I'm doing G composed with gamma. So let me make that explicit. So G is a function from Rn to R. So G composed with gamma is what kind of function?
R into Rn.
No. Remember, G composed with gamma means first do gamma, then do G.
R2.
So it's just an ordinary real valued function, right? So you can write it down explicitly. And the derivative on the left-hand side is just an explicit formula that you have been writing for many years. And I'm saying evaluate this derivative at 0. So that's something you can write explicitly as a limit. When you write that limit, you will see that it is something very familiar. And on the right-hand side, you will get something depending on what, whatever we have figured out. So the answer, so I will just tell you the punchline, right? What this is going to give you is that it will relate the gradient of G with the directional derivative of G. In which direction? You look at that curve. That curve is something that is, in which direction is that curve pointing?
And the
Down.
V direction.
V direction, right? So this is going to give you a connection between the directional derivative in the direction V and the gradient at V. All right. So simple exercise, but you should do this. Simple exercises are good because they force you to work with the definitions and then internalize the definitions. All right. So now we come to our main brief today, which is the mean value theorem. And part of the reason why I did this is one, it is a common situation, but notice that this dot product comes in. So if you have the dot product, then this suggests, and remember that when we prove things in analysis, we calculate limits or whatever, it's the lifeblood of analysis is estimates, proving inequalities, right? So we want to prove inequalities, and here is this dot product. This suggests that which norm should we use in our calculations.
L2.
Right. So this suggests that we should use the Euclidean norm because we will be able to use what? What inequality?
Cauchy-Schwarz.
Cauchy-Schwarz, because I have the dot product and I have the Cauchy-Schwarz inequality, right? So let's recall. So in view of this, so here we should say, so we will use Euclidean norm on Rn and have, so which is just recall, have Cauchy-Schwarz. What does it say? If I have two vectors V and W, then what do I know about? Okay, what do I know about their dot product?
It's less than or equal to the product of their norms.
Yeah. So in fact, we can take absolute value here, right?
Right.
So V times W. Maybe I should not put that dot there because that's just real numbers. Okay. So let's keep that in mind. This is going to be useful. Excellent. So mean value theorem. So what does the ordinary mean value theorem say? Let's recall. Recall ordinary mean value theorem. So what is the situation? You must have done it hundreds of times, maybe even literally. So if f is a continuous function on a closed interval, real valued function, continuous, and f prime exists for all x in AB, then what happens? Then there exists C in the open interval AB such that what happens? Okay, let me just write this down rather than f of B minus f of A equals, okay? Well,
B minus A times F prime C.
Yeah, F prime of C times B minus A. Okay, very good. All right. So this is the famous mean value theorem. How do we prove this, by the way? Just very quickly. So what is the proof? What gives this? What is the key ingredient? It's a consequence of which another fundamental result.
Rolls MVT.
Okay, so several answers, but so, and I don't know what you think of as the key, but I'm thinking of this as the key thing here is the extreme value theorem. So how does the extreme value theorem come into play? So really, mean value theorem is just just a little bit of playing, and you get it from the main crux of the matter is Rolle's theorem, right? So why are Rolle's theorem? You can just adjust the function, right? So that this secant, which goes from a comma f of a to b comma f of b, actually becomes horizontal just by adjusting the function by a linear function, right? So it really is Rolle's theorem. And then for how do I prove Rolle's theorem? So where do I so if f of a equals f of b, then this simplifies. Basically, I'm just looking for a place where the tangent line is horizontal. And where will it be horizontal?
At some extreme point.
That's an x, right? And so the extreme value theorem, so using f prime of extremum equal to 0. That's what the extreme value theorem is telling you. And where does the extreme value theorem come from? So you see the derivative has now disappeared. Extreme value theorem does not have derivatives. Extreme value theorem simply says that if I have a continuous function on a closed interval, real valued function, then it has a supreme value and infimum value, and it actually attains those values. So where does this come from?
Uniform continuity and compact.
Okay, so right. So okay, maybe okay. So but essentially, I mean, the basic thing is compactness, right? You have to, so the fact that the closed interval is compact, and where do you get that the closed interval is compact? Sine-Borel. So this is really okay. And so I don't know what proof you have in mind, but what I'm saying here is that the closed interval is compact and f is continuous. That means that f of this thing is compact in R, and being compact in R, what does it mean? This is closed and bounded. Being bounded, that means that this set will have a supremum and an infimum, and since the set is closed, it must contain its limit points. So the infimum and supremum will have to be attained, right? So this in a nutshell is sort of, in fact, we did some very key things in, quickly, we did some key things in your analysis 1. So now the question is, do I have something like this in the multivariable situation? So if you were to guess, so do we have an analog in multivariable situation? So if you just look at this statement, you see there are some issues. So first of all, this C that exists between A and B, there is no such thing as between. So any guesses? I mean, what kind of, if you were to guess, what kind of analog would we want? Any guesses?
An open ball with A and B as diameter points.
Right, okay. Or, really A and B, I can take inside any open set. But that kind, okay. So, but maybe any open set is funny because you see, where should this C, I mean, what, so there is going to be some function from somewhere to somewhere, and I want something, you know, everything is a moving target over here. Okay, so let me make the situation simpler. Instead of having multivariable situation on both sides, in the source as well as the target, let us first try to see the simplest situation where I still keep the closed interval AB. But now my function is not real valued, but it's a vector valued function. So first consider, let us say f from A comma B to, and if this works, then we can be more ambitious and say, okay, all right, so let us say, so do all the hypotheses make sense first of all? Continuous, yes, certainly it makes sense. F prime exists and everything makes sense. So with same conditions, So question, does there, or is there a C in AB such that? So what do we want?
Maybe we will consider norm of f of b minus f of a by norm of b minus a.
Right. So let's not divide because I mean it is given. See, we have a closed interval A and B. So if A and B are equal, then the whole thing just there is really nothing to say. There is nothing in the open interval. But still, let's keep it as multiplication rather than division. So what is the proposal is that maybe this is too ambitious. And in any case, what would this equality be? I mean, does it kind of make sense? F of B minus F of A is a quantity where hello. So F of B minus F of A
In Rn.
So this is in Rn, correct? Yeah, so this is a vector in Rn. B minus A is just a, so what is B minus A is a real number. And this F prime of C, where is that?
That's in Rn.
That's in Rn. So, okay, so this does make sense. But the proposal that was given is that maybe this is too ambitious. So perhaps what we should say is that just have this at the level of norms. But I'm sorry to have to tell you that even this is too much. It's just, the answer is no. And there is no mystery. So example. So let's take the function from R to R2, which takes any, okay, so I'm using my name for parameterized curve. So let's say t goes to sine t, cosine t. Just look. And what interval? And in fact, why R? Let's just put the interval itself over here. What interval do you think I should take?
0 to 2 pi.
Exactly. What happens on the left-hand side? F of 2 pi minus f of 0. What is that?
Zero.
It's the zero vector, right? So I will just write 0, comma 0. So what this is saying is that the derivative should be 0 somewhere because b minus a is 2 pi, right? But what is the derivative? So let's call this f. F prime of t is what? Well, so in particular, the norm of this is always equal to 1. Yeah. So the answer is no. However, what is true is that this result is true up to inequality. So I do not have equality, but what inequality should I have? The left-hand side, where I have written the question mark, the left-hand side is always going to be, I will
Less than
always
or
be
equal
able,
to?
yeah, I mean, sorry, so that came out wrong. There will always exist a C such that the left-hand side is less than or equal to the right-hand side. Okay, so this is weaker, but it is still pretty good, you see. So let me write this down. So what we have is, we have two versions of the mean value theorem. One is the situation that I just wrote, R to some Rn. And then there is another one, in which case I have a multivariable version on both sides. So let's try to do this. Theorem 1. And then the hypotheses are, let me write it once again. So let f be a continuous function on a closed interval, continuous, and f prime c exists for all c in the open interval. Then there exists c b such that exactly the same thing. F of b minus f of a, the norm of this is less than or equal to b minus a times norm of f prime c. And again, remember, the vectors f of b minus f and f of a, and therefore their difference, they are in Rn. F prime of c is also in Rn, and the norm that I'm taking is the Euclidean norm, right? You cannot say that here, oh, it doesn't matter which norm I take. Those are soft things. Whether something is continuous or not, for that the norm doesn't matter. Whether something is differentiable or not, the norm doesn't matter. For the value of the derivative also, the norm does not matter, because remember, the limit in question is 0. However, here is an actual inequality between numbers that are obtained using norms. So of course, which norm I use does matter over here, right? So let me just say here. Okay. And the proof of this is really a clever proof. So this is a proof from Rudin, and then he attributes to I think a Russian mathematician who came up with it when he was translating the book into Russian. So clever use of one variable mean value theorem. Okay. So if I want to, okay, so let's see. I mean, I will try to motivate it, but really this is like wisdom in hindsight. Okay. A revisionist history, if you will. But still, at least let's try to have revisionist history. So if I want to use one variable mean value theorem, then I have to have a function from R to R. I'm given a function from R to Rn. How can I cook up a function from that which goes from R to R? And the answer is, a natural answer is just compose it with a function from Rn to R. Yes. This is what I want to do. So here's what. So this is what we will consider R, sorry, not R. I have, okay, so I have, from here, I'm going to go to Rn, and here I'm going to go to R, okay. So the original function is given to me. So this is f, all right. So t goes to, okay, so t goes to f of t. That's a vector. All right, so let's put that on the side. So what function is there from Rn to R? Lots of functions are there, right? So these are functionals, correct? Linear maps from Rn to R. All right. Any ideas so far? I mean, if somebody has something
Maybe
quick, then you can tell me. Otherwise, we'll
projections.
go on. Is there an? Yeah, right. So right. So okay, what do you project on?
Any one of the coordinates, the first coordinate of the second.
Right. So, but you see, now the coordinates are somehow, this somehow has to be attuned to the function f, right? It cannot be just something which does not look at f at all. Okay, let's put that on the side. Let me say something else. And let's see if that helps. Okay. So what I'm going to do is see on the left-hand side, what is it that I have to bound? Okay. I have to be able to see the right-hand side is a moving target of the desired inequality because I have to find a C. The left-hand side is a fixed target, correct? So let's write this here. Want to bound this vector f of b minus f of a, correct? Its norm. So let's give it a name. That's the vector that's the vector whose norm I want to bound. Okay. So already this puts something in my mind. I want to bound a norm. I probably should use Cauchy-Schwarz. Or can try to look for using Cauchy-Schwarz. Now, if I want to use Cauchy-Schwarz, I better have a dot product, right? Now, does that tell you something? A way to get a vector in R from, a way to get a scalar in R from a vector in Rn, a method is to dot it with something. Yes. And if you want, this also is some kind of projection. If you wish, it's sort of projection by killing the plane that is orthogonal to whatever vector you're dotting it with. That plane you are killing. So you're sort of taking a component that is orthogonal to that, scaled by whatever. So which vector should I dot it with? What should that map be?
I guess f prime of c.
Okay, f prime of but okay, so that's kind of odd, you see, because f of b minus f of a, that's in Rn, right? Whereas f prime is really evaluated only on real numbers. So sorry, so say that again, please.
Yeah, like f prime of c, like the vector f prime of c.
But I don't know what C is, right? I'm trying to look for C.
Oh, okay. Yeah.
Right. So what we will do is we will just dot it with Z. So this is going to go to f of t dot Z. Very good. Okay, excellent. So let's take a look at this. So idea dot with Z and use Cauchy. Okay, I'm putting this on the side because it really is not a precise idea, right, until now. So all right, but let's take a look at this function, and I'm going to call this function something. So let's call this function phi of t. Okay, very good. Can I apply mean value theorem to this function phi? Well, we know, right? I mean, in order to do that, this function has to be continuous on the closed interval and it has to be differentiable on the open interval. So let's take a look. This function, so let's write this down here, Rn to R, and let's take a variable vector here. Let's call it something x dot z. But that what is this? This really is x1 z1 plus up to xn zn. Right? That's what it is. Is this function continuous?
It can be seen as projections. With
Yeah,
scalar
I mean, this, yeah, I mean, this is as nice a function as you could use as you would want. It's a linear function. Remember, those z's are even constants; they are not varying. So this is just like saying x1 comma x2 goes to 3x1 plus 5x2. Of course, this is a continuous function. This is a differentiable. It's all kinds of functions that you want. It's the nicest possible function. Okay. Maybe not but it's a very nice function. So this is differentiable in particular continuous. So I can apply this mean value theorem to phi, because you see it's a composition of a desired function with a desired kind of function with a desired kind of function. The second function is even a linear function. Yeah, so I can apply the mean value theorem to that. Okay, very good. So I will get, what do I get? Phi of b minus phi of a equals b minus a times some phi prime of c. All right, so now let's take a look at various things here. So let's take a look at the LHS. What is phi of b minus phi of a? Well, what is phi of b?
f of b dot product z.
Yeah, so I just apply the definition, right? So I first take f of b and take the dot product of that with z. I put z on the second slot, not that it matters. But okay, so f of b dot z minus f of a dot z. But what is that? That is f of b minus f of a dotted with z, which is the same thing as z dot z. Remember, that's what z was. It was the difference between the two, right? So let me just put maybe that in a circle here. So that is the norm of z the whole square, and things really start looking good now, right? Okay, very good. What about the right hand side? Now here it's a little bit of b minus a is okay, nothing. So really the question is, what is phi prime of c? What was phi? It was the composition of two functions, right? So let's write down. So this is really, what is phi? I first do f and then I do, oh, okay. So, all right. I see I have not given a name to that function, no? Okay, so let's give a name to this function. And what should I call it? Okay, so let's call it g here. Okay. So now you tell me over here. So this is and I know exactly what this is by the mean value theorem. This is g prime of f of c time composed with is this correct what I'm doing? Yeah, times f prime of c composed with f prime of c. Okay, very good. But what is g prime? What is g prime? So look at that map G and calculate its derivative. Okay, so first I have to see what kind of animal this derivative is. What kind of animal is this derivative? G is a map from Rn to R. So what kind of, so its derivative is also going to be something that goes from Rn to R, right? A linear map. So in terms of a matrix, what is it?
Z transpose.
Okay, so let's be, yeah, so correct. So let's take this carefully. It's very simple, but sometimes when things are very simple, they can be confusing. Okay. So this is a map from Rn to R. So its derivative is also going to be a linear map from Rn to R. A linear map from Rn to R is just a row vector, a row. Regarded as a matrix, it is a row. Yes. Right?
Yes, sir.
Okay, very good. What will be the entries of this matrix? Just look at it. The entries are just going to be partial derivatives, right? So in terms of the, let me just write down G prime of X, its matrix is going to be what? It's going to be just partial derivatives of all of that formula with respect to every single xi, just written in a row. So what is the matrix of that?
Z1, Z2 all the way
Up to Zn, correct? And regarded as a row matrix, if I think of this as a map. Yeah. So notice, does this matrix depend on X? No, it doesn't matter whichever X it is. The matrix is the same. This is just the analog. This is just saying that the derivative of a linear function is constant. It's the constant matrix. But look, this can be seen in so many different ways, and they're all really the same. Look at the kind of map G is. What kind of map is G? That itself is a linear map. Yes? Just look at the formula. Dotting with any given vector, it distributes, no? Dot product distributes and scalars come out. So G is a linear map. What is the derivative of a linear map at any point?
The map itself.
The map itself, but that's what I've written down, no? The matrix of this map, when I write down this dotting, it is really dotting with the vector Z, right? But if I want to write it as a composition, then I need to write it as a row because it needs to be matrix product. Okay. So what is happening over here? Let me just go back for a moment. It's the exact same type of idea that happened over here. When I did the special case of the chain rule for a curve, if I wanted to think of this chain rule in terms of a matrix product, then it was a row vector times a column vector. The row vector that I wrote down in terms of Z's, that's the row vector. But I can write the same thing as a dot product. So what is the upshot over here? The upshot over here is really, this is the same thing as Z dot F prime of C. Easy. Make sure you get it transparently. Okay. All right. So all that remains is to gather the fruits of our labor. So what is the right hand side? So what this gives is, what this gives is, remember the left hand side was just, so we have norm of Z the whole square, Euclidean norm is B minus A times, so Z times F prime of C. Okay. So what do I do now? This is where Cauchy-Schwarz comes in. And this gives me that this is B minus A times the norm of Z times the norm of F prime of C. And what do I do finally? Come on, just see the ends now.
Either norm Z is 0, in which case we already were done, or we divide by norm Z.
Correct. So just look over here. If norm Z is 0, then that just means that F of B is equal to F of A. then the inequality that I want, there is nothing to prove because the left-hand side is 0. Yeah. So may, I'll just put here, may assume, or maybe I'll just write down, nothing to prove if z equal to 0, else cancel and we finish the proof. Okay, this is a very small but very clever proof because you had to get this idea. All right, so any questions so far? All right, so we're now going to bootstrap this into, so this we call this theorem 1, right? So we have now a theorem 2, which is the following version. All right, so it's a multivariable version. So I have let, I'm going to take an open set U in Rm, and I have a differentiable function on U going to Rn, right? So there is something else that is going to be required, but we will come to it. So f differentiable on all of you. So I'm still going to take A and B, but now A and B will both be in U. Okay. There is some more hypothesis which which I have to write down still, but then, so some more hypothesis is coming. And for all A and B in U, I still want to bound this f of B minus f of A less than or equal to something times B minus A. Now, you see, A and B now are vectors. So I cannot just write down B minus A, the side of an inequality. There has to be a norm over there, right? The point is here, I say M, where M is some kind of global bound on the derivative that is given to me. So, and f prime of x is less than M. So of course, that means I have to take the norm, Euclidean norm for all x in U. Okay. So then this is the statement. This statement is still not correct. There is still something missing over there, but let's try to discover it in the proof. And the idea is, as is often the case in mathematics, you build a stronger theorem on top of a special case that you have proved before. So we are going to use theorem 1. And that tells you that something, you see, A and B is given to me. So this sort of is just writing itself. So A and B are fixed. That means I can take the interval from A to B, right? So I want to do the same thing, but I want to have a function now from real numbers. Okay. So let's see what this result over here is, right? So I can see I have an inequality like that. Where the source is just a closed interval in real numbers, and then I have a function. So how can I reduce to that situation? Here A and B are vectors. Okay, so there is no mystery. What I do is I just fix a curve from A to B, a parameterized curve, right? So given A and B in U, take gamma from 0, 1 to U, which takes any t, it starts out at A and ends at B. So what is the standard way of doing that? This you must have seen in school. You want to start out at A, so A plus, and when t is equal to 1, you want to land up at B. So what do I do?
T times B minus A.
Standard, right? Standard parameterized curve. And at this point, you should howl in protest.
We need convex U.
Yeah, so you see, I merrily wrote this gamma is a function from 0, 1 to U. See, if I want to apply the, apply to what? The composite function 0, 1 to U to F to Rn, right? I need the target of this set, this entire target to be in U. Because otherwise, what is the meaning of the composite function? The F is defined only on U. So if I want to apply this function to U, then for every value of T, the image of this map, this entire curve gamma has to lie inside U. But that precisely saying if this is to happen for every A and B in U, then that means that the set has to be convex. It's just definition, right? That if any 2 points are there, then the straight line segment joining the two points has to be within the set. So that has to be written here, convex. Right? So this is valid. So this is valid by convexity. So I'm just going to say valid by convexity. Valid, that is the fact that the target is in U is valid by convexity. So I apply the mean value theorem to this composite function. And now I just write it. So what do I get? So to the composite. So I call this G. So what do I get? I get some C between 0 and 1. Maybe C is a bad idea because you see, it can cause cognitive dissonance. A and B are vectors here, right? So maybe I should take some T. T in, and also strictly speaking, I mean, this is okay, but really I can say something more. It's in open interval 0, 1, such that what? So let's just do this. Such that G of 1 minus G of 0. Oh, by the way, this whole function is also satisfies the property because the initial function is just a line, you see. A straight line segment is, of course, a different, I mean, it's differential everywhere. It's, yeah. So there is no problem. So the composite function also satisfies the hypothesis of the mean value theorem. Okay, so let's just gather this. No, so what is, so what do I get? This is less than or equal to some G prime of that T norm times 1 minus 0. So that 1 minus 0, I can just forget. But what is that? So what is G of 1? I mean, just look at the composite function. What is G of 1? That is F of gamma of 1. But gamma of 1 is
B.
Come on. It's B, right? So this is just I. So this is F of B minus this is F of B minus F. Exactly. So this is just E. That is B prime of gamma of T. Now times gamma prime of C. And again, it's going to be the same thing. You see, I mean, you can think of this as a dot product of two vectors. Sorry, no. The target is in Rn. So, okay. So my bad. So this is just going to be composition, right? But let's see what this is going to be. So F prime of gamma of T. Now F prime of gamma of T is going to be
Sir, there is a norm.
Help me over here.
Sir, there is a norm here.
Yeah, sorry. Yeah. There is a norm. Absolutely, there is a norm. So Okay. So f prime of gamma of C is okay. So the point is okay. So, but the point is note. So note. What is gamma prime of C? Sorry, no, what am I writing here? Not C. F prime of gamma of T times gamma prime of T. So what is gamma prime of T? Gamma is a line.
B minus A.
Yeah, so just look at this. I mean, pretend it's a linear formula, right? Constant plus T times a constant. The derivative of that. So if you want, you recall, this is like an affine map. The A goes away. And gamma prime of T is just B minus A. All right, okay. So what gives now?
So then I guess gamma prime of T comes out of the norm, and we anyways have a bound on F prime. So
Yeah, right. But you see, now I'm a bit confused over here. That's exactly what we want. So let me just write this down. So this is precisely because that is bounded by so okay. So this is, and gamma prime of T is B minus A. So I can just, so this is what I want to write. Yeah. Okay. So now I understand. So, but justify this step for me, please.
Sir, gamma prime of T is a constant, so we can just take it out of the norm with like a mod. So
Yeah, but you see, it's a constant vector.
right, yeah, but we can actually, I think we can
You
do
see,
norm.
I mean, you see. I mean, the point here is the following, right? There is something to be done over here. So I'm sorry, I had sort of overlooked this point. See, really speaking, when I write f prime of gamma prime of T, what is that thing? What is the operation between those two? It's composition, right? Remember, both of those are operators. They have matrices. Yeah. And gamma is a map from real numbers to U. So it's a so its derivative is going to be a column vector. That B minus A is just a column vector. Whereas F prime is really going to have a matrix. So this is a matrix times a column vector. It's a matrix vector multiplication. Yes.
Yes.
So I have to have some kind of but this is okay because you see, okay, so this is something to write down. You remember that so this is, so here I'm yeah, so remember that this is something or the other about operator norm being used, right? So yeah, I apologize, I completely missed this point. So remember, for the operator norm, the norm of the vector a applied to V was related, right? Remember, that was less than or equal to the norm of A, operator norm of A times the norm of V. Yes. See, how is it that I'm suddenly splitting those two? There has to be some justification for that, right? So let me just say at this moment, okay, so because I do want to use the last 5 minutes or so to move forward. So let me just say that this is a matrix vector multiplication. So we have to justify this. Basically, what is happening is that you're separating that norm of this composition or the product, the matrix vector product, into norm of the product of the norms of the individual things. That has to be justified. All right.
Yes, sir.
Okay. So we'll sort it out right in the beginning of the next class, but I do want to sort of move forward a little bit and orient you to something. Okay. And that goes about as follows. Okay. So far, here is the thing. I mean, a derivative as a function. That's a very misleading thing because the derivative is a function, right? But the point is, let me just, so. You see, if I have open set U in Rm to Rn, then df of A is a linear map if it exists, okay, from Rm to Rn. df of A is an element of L Rm Rn. But what I'm saying now is that if I let A vary, if f is differentiable at each A in U, then I get a function from that takes A to df of A, which is the same as f prime of A. So this is a function from where to where? Well, A is in U, so this is a function from U. And what is the target? Every element, see what comes out as the output of this is a function, right? So this is a map from, remember the derivative at A is a map from Rm to Rn. But if I let A vary, then for every A, I am getting a map. So this map df is a map from where to where? The input is a point. Oh, sorry, this, I should not write this. So df is a map from where to where? The input is a point and the output is a linear operator from Rm to Rn. So you see our viewpoint changes. Even in one variable, you do this, no? In the beginning, when you are just, taking those secant lines and then moving one of the points close to the other one, you are really calculating the derivative only at a fixed point. Your laser focus is only on that point. But once you do all that, you say, okay, now that is done, and now I can do the same thing at every point and get derivative as a function. We are doing exactly the same. But here, the value of the derivative is not a number. The value of the derivative is a matrix or a linear operator. So as the point A in the domain varies, if the derivative is defined at every point, then I get the derivative of f function whose inputs are points in the domain and whose outputs are linear operators. So df is a function from U to the space of operators, but there is nothing to be scared of this because the space of operators itself is a vector space, no? So this is a vector space of dimension, what? Come on. Mn, exactly. So dimension Mn. Therefore, now I can start thinking about, can ask about continuity and even differentiability of this map df. So conceptually, some of this is like what you did before. No, you merely took double derivatives, triple derivatives, whatever, right, in school. So that's all that's what is happening here. But the targets are changing. Okay, so let us postpone the consideration of differentiability of df till later. Let us just first worry about continuity. And I'm okay. And these notions are independent of the norm chosen on L, which is isomorphic to Rmn as a vector space. So of course, often I will use the operator norm, but I can use different norms depending on what is convenient for me. So let me just state the goal and then we will stop. So we will consider C1 of U. So this is by definition all functions that are differentiable at each A in U, and df is a continuous function. So we say that, i.e., in short, we say C1 of U is the space of, or the set, let's not call it space, continuously differentiable functions. And you know from real analysis that just because a function has a derivative everywhere does not mean that the derivative function is continuous. And you must have seen examples of this. So our goal is the following. This is the result that I wanted to get started with, but let me just state it. A function f from U to Rn is continuously differentiable if and only if all partial derivatives DIF exist at each point, at each A, and crucially, and are continuous. So if you drop the continuity requirement on either side, then these two things are not very well related to each other. There's only one way implication. But so what you should do is homework. So see that exercise. See that the forward direction is easy. Try to read proof of backward direction, which nicely uses the mean value theorem. Okay, so since we are out of time, we should stop.
Recording stopped.
Okay, so I'm already out of time and I have to sort of leave early today, but if there are any questions, then I can try to answer them. Okay, so very important announcement. The exam, of course, will not happen on Monday. It will almost certainly not happen the following week also, because I have now almost ready with the work that I want to give you, and I want to give you enough chance to do that work. So it will not happen the following week. So it will likely happen in the last week of this month. And as I told you, there will be an oral component, which from my point of view is the more important one, because I want to see how everybody thinks.
Here U bar is just the closure of U, right?
Oh, sorry. I'm very sorry. I should. I just wanted to underline that and for emphasis. So continuous on you. Right? I mean, the function is defined only on you. So the thing outside that makes sense.
Sir,
Yes.
so could you scroll up once again?
Yeah. So to what place?
Yeah, right here.
Okay.
Yeah, you have written justify this. Like, why can't we just use operator norm? Like the
Right.
property?
Okay. The thing that, yeah. So the thing is, okay. So we can use operator norm on f prime of gamma of t, right? F prime, remember f prime of gamma of t is an operator. So I can use the operator norm on that. Yeah, okay. So I guess, yeah, so very good point. And so what I did not appreciate is that in the hypothesis, when we said that f prime of x is the norm of f prime of x is less than m, what is f prime of x over there?
So it's a vector in Rn.
No, you see, f prime of x, for every x in U, f prime of x, remember the derivative is an operator.
Yeah, sir. And then when we
Right.
like take
So this is the thing that my brain also just sort of blanked out over there. The meaning of the hypothesis itself is that when you are given a bound, the bound on the derivative is under the operator norm. Yeah. So thanks for pointing it out. So this issue is solved for us, correct? So let me write this down in, yeah. So bound, okay, so not, forget the bound doesn't matter, it's no norm, okay. Operator norm on f prime of x. Okay, and now if this is the case, then I'm done, because I should just insert a step in between. So when I put this up, I will just clean it out. Okay, but there is an in-between step which I don't have space to write, but let me just write that here. So you see this really, so you can think of this as operator norm of something b times a or s times t, whatever we wrote. So this is less than or equal to the norm of f prime of gamma of t times the norm of the vector. Remember, gamma prime of t is just a vector, right? This is something that we proved, that the norm of an operator a applied to a vector v, that is the norm of that vector, is less than or equal to the operator norm of operator a times the norm of the vector v. We did prove that. This was a very easy thing. I think that was the very first property, in fact. Yes. The only extra thing to recognize here is that the operator norm of gamma prime of t is really the same thing as its Euclidean norm, because it's just a column vector. You see, the composition is as operators, no, but it really is a matrix vector product. So there is nothing much going on over there. Yeah, so good. Thanks for sort of pointing it out. Is it okay? I think this issue is now resolved. We don't have to say justify this. When I put up the notes, I will clean it up over here. Okay, anything else? Yeah, so now let me ask you a question. Unless there are, how many exams do you have next week?
CA
3.
students have 3.
Hmm.
I am not sure about physics.
Okay.
Oh, we have 4. Sir.
I have 4 exams. So honest answer, all right? And maybe in fact, I would like the class rep to to conduct a survey and get back to me, because I don't want to put pressure. I think I just want to see I mean, I know there will be howls of protest if I say that let's have a class on Monday because we are not going to have an exam. I just want to know, how shrill and how vociferous the protests are. If people are okay to just to have a class, a majority of the people are okay to have a class, then I would like to have a class. But if there is strong protest, then okay, then we will forget it. All right. I'm not a very unreasonable person. I'm only somewhat unreasonable at times. So will you guys let me know maybe by the end of today or over the weekend? Yeah. So I'll tell you what we will do. Okay. Because one part of the development we will finish on Friday. Anyway, right? On Friday we are going to have a class. So this theorem that I stated at the end, that theorem we will do on Friday, and that is sort of that sort of brings that's a certain nice point in the course where what we have done is much of the things that are common to much of the basic stuff is done. Then there are important theorems like inverse function theorem, implicit function theorem, equality of mixed partial derivatives. And if we were to have a class on Monday, I will not do anything of that nature. What I would do is maybe answer questions and just do a whole bunch of examples, because so far we have really not seen very much by way of how things can go wrong or what other kinds of behavior is seen, right? Remember I wrote that in color earlier, that what changes, what stays the same, and what kind of new things do you see. So if you have a class on Monday, then what I would do is answer questions and maybe do some examples. But you let me know. Okay. All right. So anything else?
Sir, could you say again the thing with the norm that we did right at the end, like about the operator norm? So the bound is given in terms of the operator norm.
The point, because there is nothing else that makes sense, right? I mean,
but I think it does work for Euclidean norm also.
Right. Correct. No, what I'm saying is, but if I use the Euclidean norm on F prime, if I think of it as a matrix and if I use the Euclidean norm, then I have to have then it has to work over here, you see?
So I think it does, because that thing inside, we can write it as a dot product and use Cauchy-Schwarz. And I think that
but now be careful, because what it is the dot product of every row of F prime of gamma of t with gamma prime of t. Because F prime of gamma of t is a matrix, remember? It's F is a function from U to Rn.
Oh, okay.
Right?
Yeah, okay, sir. Yeah.
No, I mean, it may still be right. I do not know, but some reasoning has to be done over there. Right? Whereas if we take the operator norm, then we have just seen it. The only extra thing to see over there is that composition over there as operators is really the same thing as matrix vector multiplication. But that is okay. I mean, we've seen that. No, remember gamma is a curve.
Yeah.
So the derivative of gamma is just a column vector.
Yeah. Okay. Yeah. Thank you, sir.
Okay, good. So, all right. And again, I think something like between 5 and 10 people in class have not met me. And those people, I really do want them to meet me. So tomorrow I will have office hours. Okay, otherwise I'll just send a mail to those people. So you will hear from me. And as always, if other people also, if you have any questions, just feel free to, certainly during office hours, just call me, or even during other times, just call me anytime. Okay, good. So let's stop for today, and then we will continue on Friday.
Thank you, sir.
All right, bye.
Thank you, sir.